Hello everyone. So we have been discussing different techniques, particularly nuclear analytical techniques, last few lectures like neutron activation analysis, ion beam analysis, wherein we utilize the nuclear phenomena to determine in analytical chemistry to determine the concentrations or even to depth profile that elements in a matrix. As you recall, we called nuclear chemistry as a subject where we use chemical tech tools like radiochemical separations, to understand the nuclear properties of elements, nuclear phenomena. And radiochemistry, as we use radiations emitted by the elements to study their chemical properties. Today, I am going to discuss a topic of research, the frontier research, wherein we use the nuclear phenomena in understanding problems in physics and chemistry and other areas. So the nuclear chemistry has thrown some probes, which we will discuss in today's lecture. Those probes we can utilize in understanding processes and phenomena in sciences. So these are, we call them as nuclear probes. Let us see what are these nuclear probes, and especially in chemistry. Of course, now we do not have a well-defined boundaries. There is a lot of research in the multidisciplinary research. We have chemical physics and physical chemistry, and that the boundary of physics and chemistry. So when I say nuclear probes, it can be applied to physical chemistry, chemical physics, and so on. So that there are three techniques which are coming in the category of nuclear probes. One of them is the positron annihilation spectroscopy. I will discuss the more in detail. The perturbed angular correlation spectroscopy, PAC. And the third is Moss-Bauer spectroscopy. Some of you may be knowing about Moss-Bauer spectroscopy. Moss-Bauer spectroscopy relies upon the required less absorption. A low energy gamma is emitted by a nucleus in its excited state, and the same gamma is absorbed by another nucleus in the sample. So the source is emitting that low energy gamma, and the sample is absorbing. And to take care of the recoil and the Doppler broadening, the sample is kept in a crystalline state and also at low temperature, and the source is moved towards the sample at different velocities to take care of the Doppler. So all these things are coming in the category of Moss-Bauer spectroscopy, and which is quite popular, but that has got a limitation on the number of nuclei that you can use. Like, for example, iron 57, you can study the iron chemistry or tin chemistry, hafnium chemistry. Certain nuclei are amenable to Moss-Bauer spectroscopy. So I will not discuss this particular topic. I will discuss the positron annihilation spectroscopy and perturbed angular correlation spectroscopy. Okay. So first, let me discuss what is this positron annihilation spectroscopy. And I will give you an example of a source, radioactive source, which emits positrons. You can use a positron source, positron emitter. Of course, it should have sufficiently long half-life so that you don't need to change the sample repeatedly. And what is the how this positron can be made use of in understanding chemical processes or physical processes? This let me try to explain using this slide. So when this positron is emitted by the radioactive source, then this positron, like if you recollect the interaction of fast electrons and positrons with matter, it is the energy of the positron will be a few hundred keV. Now this positron will slowly interact with the electrons in the medium, and it will slow down by its elastic scattering, and the slow down. So when it becomes thermalized, a positron which is thermalized undergoing a tortuous path, then this thermalized positron can undergo different types of interactions. So one of them is annihilation with an electron. The positron is thermalized, it has no momentum, and when it is annihilating with an electron, you get 2 photons of 511 keV each. The rest mass of electron-positron pair is 1.02 MeV, and so that leads to the gamma ray photons 1.02 MeV split into 2 photons 11 keV each. And because the initial momentum is 0, the 2 photons are emitted at 180 degree. We call them as annihilation gamma rays. Now what happens that if the electron with which the positron is annihilating is not stationary, it has some certain momentum, then the positron annihilating with an electron which is in motion and hence has some momentum, that 511 keV gamma line will get broadened. That means it will not be exactly 511, it will be 511 plus minus delta E because of the momentum of the electron. And so there comes the technique called positron annihilation, Doppler broadened annihilation radiation. So this 511 keV gamma ray is broadened because of the Doppler broadening because of electron momentum. And we can make use of that broadening to determine the electron momentum. Secondly, these two 511 keV gammas are 180 degree angle because of again the same process, that is the conservation of linear momentum. And so the angular correlation between these two gamma rays, that means if you measure the coincidence counts as a function of theta, W theta versus theta, then we should get a line at 180 degree. But because of the electron momentum, there is a angular correlation. So more than plus minus 180, there are some counts. So this angular correlation, deviation from 180 degree, is again because of the momentum of the electron. So you can study the electron, what type of electrons are involved when the positron is annihilated. So these are the two techniques: Doppler broadened annihilation radiation, DBAR, and angular correlation between annihilation. So we will not talk about this angular correlation, so it can also be used to obtain the electron momentum. And third technique is like when the sodium-22 decays by beta electron positron to this excited state of neon-22, this is given. So the lifetime of this intermediate level is, the excited level is very, very short. So in less than a picosecond, and so this 1270 keV gamma, 1275 keV gamma is emitted almost instantaneously upon the decay of sodium-22. So we can say that this 1275 keV gamma ray tells you the time when the positron was born. And subsequently, the positron is thermalizing, interacting with the electron and annihilating with the electron to give you a 511 keV gamma ray. So that tells you the death of the positron. Positron is finished now. And the time difference between these two is called the lifetime of positron. So depending upon the environment, chemical environment in which the positron is dying or positron is annihilating with an electron, this lifetime can change. And so this lifetime essentially tells you about the electron density in the medium where the positron is annihilated. So this is another experimental technique. If you can determine the lifetime of positron, how do we determine the lifetime? The time between 1275 keV and 511 keV gamma rays. So I will explain the instrumentation for this lifetime spectroscopy. So these are the three experimental techniques: Doppler broadening of annihilation radiation, angular correlation between gamma rays, and lifetime spectroscopy, which are used in positron annihilation spectroscopy. And one of the, other than this electron momentum and electron density measurements, another very interesting field is positronium chemistry. See, the chemistry of positronium. Positronium is an atom similar to hydrogen atom. In hydrogen atom, you have a proton and an electron. Reduced mass of hydrogen atom is 1 mass of electron. Reduced mass of positonium is 1 by 2 ME, M1, M2 by M1 plus M2. And so, accordingly, the binding energy or the annihilation potential of the positonium is 6.8 electron volt, which is half of the hydrogen atom potential, 13.6 electron volt. The radius of hydrogen atom is 0.54. The radius of positonium is 1.08. So double of the. So you can see the beautiful chemistry of positonium atom. So when the positonium atom is formed, the positonium means a positron and an electron. So depending upon the spins, if they are antiparallel, so you form a singlet state. Antiparallel spins of positron and electrons called singlet state or parapositonium. And this is the ground state of positonium. And there is the orthopositonium, triplet state, where both these spins are parallel. So this parapositonium has got a much shorter half-life of 125 picosecond, which you can determine from this lifetime spectroscopy data. And this is disintegrating, this decays by 2 photons, that means 2 511 keV gamma rays. So that is the normal positonium decay. Whereas the orthopositonium is a triplet state of a positron and electron, and in vacuum has got a lifetime of 140 nanoseconds, so very high lifetime. And since this has got a spin of 1, though if it has to decay on its own, it decays into 3 photons, 1.02 MeV upon 3, about roughly about 370 keV each photon. But what happens now? Till 140 nanosecond, it is very difficult, highly improbable that positonium will remain as a orthopositonium. Before that, it undergoes different types of reactions like pick-off, oxidation, spin conversion, and so on. And so you see an orthopositonium signature in a higher component. Instead of 125, you may have 150, 200, 250 picosecond lifetime. So this is the another area is chemistry of positonium atom itself. These are the 3 techniques by which you can do study with positron annihilation spectroscopy. So let us discuss in more detail these experimental techniques of Doppler broadening and lifetime spectroscopy. So as I mentioned, the finite momentum of the electron-positron pair, when the pair is annihilating, leads to the Doppler broadening. And so instead of 511 keV, so we call the typical gamma spectrum of the determined using a germanium detector. HPG means high purity germanium detector has got very high resolution. And so you will see that 511 keV, if you have a source emitting 511 keV, not positron. The positron emitting source also gives 511 keV, but there are sources which emit 511 keV gamma ray after the decay of the parent. So that gamma is much narrow. And so this is the inherent resolution of the detector for 511 keV. But because of this Doppler broadening, if it is a positron, if this peak is due to the annihilation gamma ray coming from positron annihilation, that this peak becomes much broader. So, and it is significantly broader. It is not that you don't see it. In a gamma ray spectrum, if it is due to radioactive decay, you will see a much narrow peak at 511. If it is due to Doppler broadening, positron annihilation, you will see a much broader peak. And so, if you can determine that wide broadening of this 511 keV peak, you can study the momentum. So the instrumentation for this Doppler broadening annihilation radiation is, you have a germanium detector, high purity germanium. It has to be cooled at liquid nitrogen temperature 77 K to take care of the leakage, to reduce the leakage current. Then you have the amplifier, and then you put it to the multi-channel analyzer through ADC and so on. So this MCA spectrum gives you the 511 keV gamma ray, and if you measure the width of this, so instead of the width, you see different parameters, which I will explain in the next slide. And from this simple gamma ray spectrometry setup, but it has to be highly stabilized gamma ray spectrum, because you are looking for the broadening over 511 keV by few electron volts broadening, or maybe 0.5 keV or so. So how do you get the momentum of the electron? So the momentum of that photon is given by h nu by c. Momentum of the photon is E by c. And so if h nu 0 was the 511 keV and h nu is the Doppler broadened, then you have h nu c minus h nu dot c, and into 2 delta E. So it is delta E into plus minus, so 2 delta E. So 2 delta E by C is P, and so the broadening is Pc upon 2. So you can determine from the broadening the momentum of the electron. That is the methodology for Doppler. So in Doppler broadening, what is important is the line shape parameter. So this is a typical 511 keV gamma ray, and you can see the 511 keV gamma ray FWHM will be here. So if the FWHM of a normal gamma ray is 1 keV, you will see it at 2 keV or so. You can see from 510 to 512. And so there are certain parameterization called S parameter. The S parameter is defined as the width, the area under this graph up to certain width upon the total area. So area of the pink shaded area upon the total peak area is called S parameter. So essentially it tells you the momentum of the valence electron, because these are the low momentum events. Whereas if you take the tail part of the 511 keV spectrum, this tail part is expanded here, and you take this parameter, then that area upon A0 is called W parameter, the white part, and that gives you the momentum of the core electrons. So you can try to get from the Doppler broadening the valence electrons and core electron momentum from the Doppler broadening of annihilation radiation. In fact, from the normal DBAR experiment data, it's difficult to get the W parameter, because the W, this width is in the tail part of it, the wider part. So the tail, you may have the content due to other high energy gamma rays, or there can be background, so background will be more. So if you can reduce the background by some technique called coincidence Doppler broadening, then you can have more accurate data about the core electron moment. So here, this is again the Doppler broadening spectrum. So this was the normal, this is the same as this spectrum, where you just have an HPG detector and record the gamma spectrum of 511 keV around that. You can see here 500 to 525 keV is the region of interest for the annihilation radiation. But what you do, if you put a sodium iodide thallium or scintillation counter in coincidence with the germanium detector, so this particular spectrum is gated by a coincidence between two 511 keV. One 511 is the measured in HPG, and other one is just in this other scintillation counter. That will trigger this gamma spectrum. You can see there is a significant reduction in the background. And on top of that, if you have two HPG detector, and then you gate this Doppler broadening spectrum, in fact, this 511 keV gamma, you in coincidence between the two HPG detectors, if that is gating this gamma spectrum, then you can see there is a significant reduction in the background, and you can study these are the core electron momenta because of coronal momentum. So you can achieve the core electron momentum distribution in the coincidence Doppler broadening. So normally a laboratory which is doing positron spectroscopy, they will be having a coincidence Doppler broadening setup. Another technique I was mentioning is the positron annihilation lifetime spectroscopy. And you measure the lifetime of a positronium or positron by a setup called fast slow coincidence setup, where this 1275 keV gamma ray is triggering the start, and the 511 kV are triggering the stop. So you have to have a circuit by means of which you determine the time difference between two gamma rays, 1275 and 511. So what you do, you have a single channel analyzer where you get the gamma ray 1275, another single channel analyzer, you get 500 kV gamma, and you in fact take a start signal and you take a stop signal from time to amplitude converter. The time to amplitude converter converts the signal into time into voltage signal. So the time gap between these two detectors for an event is converted into a voltage signal by this unit called time to amplitude converter tag. And this tag then spectrum, the tag output is an output, analog output, which will get you the time spectrum. The x-axis is the time and y-axis is the counts. So this kind of a coincidence setup, it is called the fast slow coincidence setup. So when we say fast means time signal, slow means energy. So you have one circuit for energy to get the gamma ray 1275 and 511. And you have one circuit for timing. You have fast signals coming from the PMT of the two detectors, wherein you put them into tag at start and stop signal and you get the tag output. Now this output looks like this. You can see here, this is called the time spectrum, counts versus time. What you get is a fast rise and slow exponential decay. That exponential decay shows multiple exponential decays. The counts is a superposition of maybe two or three exponentials. So every component has got the intensity I1, I2, I3, and a tau, lifetime, tau 1, tau 2, tau 3. So you can fit this data into multi-exponential curve and get the constants II. So what you get the output is II and tau I. So I1, I2, I3, tau 1, tau 2, tau 3. Tau 1 and its intensity is I1. So what do these lifetimes represent? They are called lifetime components. This tau 1 is actually that 125 picosecond, that is the lifetime of the parapositonium. That is the shortest component. So when the parapositonium annihilates, you get 125 picosecond. So the first shortest lived component will be parapositonium annihilation, and it does not really give you any chemical information because the time is too short. The second one is the tau 2. After more than tau 1, you have tau 2, and it tells you the free positron or positron molecular species annihilation. So it is actually a sort of a peacock. The positonium can interact with a molecular species and undergo changes. So that will increase the positron. When your positron is binding with a molecular species, lifetime will increase, and that gives you about the chemical species that is formed. And third is tau 3, that is the orthopositonium annihilation. Orthopositonium lifetime is 140 nanosecond, but this tau 3 is not 140, it will be few nanoseconds. So you have 125, another one maybe 150 to 200, something like that, and tau 3 is the longest lived component that can vary depending upon the type of material that you have. So what information you get from positron annihilation lifetime spectroscopy? The orthopositonium lifetime 140 nanosecond is decreased by peak of annihilation. That means when you have a orthopositonium where both electron positron spins are parallel, it can pick off this electron can be picked up by a chemical species, and it will annihilate with another electron. So this essentially tells you the electron density, or suppose you have a zone in which there are not many electrons, the positonium will survive for more time. So the orthopositonium lifetime depends upon electron density. If electron density is high, lifetime is short. If lifetime is high, electron density is low. So like a defect, The defect is not, there are no electrons in that defect size. So positonium will go and sit there. It will prefer to stay in a site where there are not many electrons. Like in metals, you don't see tau 3, you only see tau 1. So it tells you about the electron density or even pore size. In polymers, when there are pores, so polymers will have areas where it can be open or closed, and the positron has a tendency to go and sit in the pores so that it can survive longer. And so the lifetime essentially tells you the pore size. Defects gives, wherever the electron density is less, that means it is a defective site, so it will give you the defect concentrations. And the phase change in terms of polymers, if there is a change in the polymer pore size, it is going through a phase change, then it can tell you about the pore size. The change in pore size or essentially phase transition. Like certain plastic materials can undergo changes, so that it can tell you about different phases. That's like glass transition in plastics can be monitored. And of course, the positonium chemistry also can be, like positron can undergo oxidation. The electron is taken up by the metal ion, and you have a positron. Similarly, it can undergo spin conversion with another chemical species. So positonium chemistry itself is a subject. There are books on only positonium chemistry. So you can refer to, if you are interested in doing research in positonium chemistry or positron annihilation spectroscopy, one can go to the literature and read the books. So what are the areas in which one can do research using positrons? The major areas of research include solid state condensed matter physics. You can study positron analysis spectroscopy in metals, alloys, semiconductors to determine their electronic structure. Like if you are determining what are the bands, due to the metals and semiconductors, you have the different bands overlapping. Which electrons are participating in these bands? You can study the momentum of electrons by Doppler broadening of annihilation radiations. If you are going to study defects, you can go to lifetime spectroscopy, and that essentially the defects can dictate the properties of materials. So you can analyze the properties of materials through characterization of their defects. So in fact, defects play a big role in governing the properties of different types of material. There can be optical property, electrical properties, and so on. So it is a vast area when we can study defects by using lifetime spectroscopy. And you have the positonium chemistry, the positonium atom formation mechanism, how the positonium is being formed in different, like for example, water and benzene. You will find that the positonium formation is different in water and benzene. And their reaction processes, like what is the chemical reactivity of positonium atom towards different species, and the dynamics of the positonium atom formation. And this is associated with the applications in molecular solids and liquids. So is another area where you can study the structures of polymers, catalysts, surfactants, liquid crystals, and so on. Wherever you will find that the molecular arrangement in the sample is going to change, so that will affect either the pore size or electron density. So that will affect the positron lifetime. Now there have been several advancements in the techniques of positonium annihilation. So there are now positron beams. From the sodium-22, whatever positron is coming out, you can thermalize and then accelerate to a required energy. So you can have monoenergetic positron beam of energy 5 electron volt to 50 keV. And these positrons of monoenergetic energy can be used in depth profiling of defects, characterization of thin films. So whenever there is a energy dependent process, you can do the study using monoenergetic positron beams. Not only, it is not that you have only sodium-22 as a source of positron. You can have copper-64 in a reactor, or you can have positrons from electron accelerator. You can stop the electrons in a high-jet material, produce brimstone, and that brimstone upon pair production will give you positrons. Or you can have positrons generated in situ. Suppose you have a high-energy gamma ray produced in a nuclear reaction, and you stop that gamma ray in your material of interest. Then you can do in situ, that gamma ray will produce positron annihilation, pair production, and the annihilated 511 keV spectrum, you can find out the electron momentum in the material. So a lot of high technology materials have been also studied using the in situ, the positron annihilation spectroscopy using in situ gamma ray. So just to give you examples of positron annihilation spectroscopy, by Doppler broadening, as I mentioned, you essentially get the momentum of electrons, and if you do coincidence Doppler broadening, you can do momentum of core electrons. So you can see the fraction of positrons annihilating with core electrons by coincidence Doppler broadening can be obtained for different metals, aluminum, silicon, and germanium. You can study in all types of metals how the positron is annihilating with core electrons and valence electrons. So the role of core electron, valence electron in positron annihilation can be studied. And this in turn, you can actually characterize an element by the core electron momentum. So suppose you have a sample from the core electron momentum, you can find out which, so you can index the metals, Z of the particular element you can index. And another example is the lifetime. From the lifetime spectroscopy, you can find out the pore size distribution. This is the radius of the pore. So certain materials like like polymethyl methacrylate is a polymeric material which will undergo changes in the pore size distribution with temperature. And you can see the pore size distribution is changing with the temperature. So how the polymeric material is undergoing changes, the internal transitions in the polymeric material can be investigated by pore size distribution study using lifetime spectroscopy. So these are just to give you examples of what you can do, but you can take a topic and see how positron annihilation can be utilized in the study of a particular topic. So there is a vast area of research in using positron annihilation spectroscopy. So I'll stop here and take up the next part in the next lecture. Thank you very much.